Hello everyone, my name is Naren and in this session let's talk about how to solve boggle or let's try to solve boggle problem. Recently I was talking to one of my friends from Bangalore who gave interview at facebook.com. While talking about different kind of questions asked in facebook.com, one interesting question came up. That is how to solve boggle. The question is something like, given a 4x4 array with different random letters in the matrix, how do you find out the valid words or the valid combinations of letters which forms a valid word? The interviewer might give you a list of words which has valid words in it, and only few of the words can be formed in this matrix. The rule is something like this. You can start from any cell in the matrix and you can traverse through any different direction. But the only constraint is that you cannot go to the same node multiple times. Only once you can traverse. Having said that, you can think now the maximum possible length of the word can be 16. That is 4 cross 4 or n cross n given a different kind of matrix. And the minimum length of the word will be 1. Sometimes interviewer might give you a list of words from which you have to find the valid word which you can form in this boggle, or sometimes interviewer might say that you have to find the valid words. If they don't give any words list, then what you need to do is you need to somehow get all the possible valid English words. How can you do that? If you are using Python, from NLTK library you can do corpus.words. You get all the valid words in the English dictionary. Otherwise, in the internet, you can download the dictionary, which is easily available as text, and you can convert it to list of words. Now, how to solve this problem? Clearly, the problem has two different subproblems in it. Let's try to solve each subproblem separately, and then we arrive at the complete solution. So the first problem is the graph problem. If you see this particular matrix, it is clear that they look like a graph. How? The question says that you can traverse through different direction possible from any cell of the matrix. For example, if you are at this cell, you can traverse to how many different possible directions? That is 8. That is 1, 2, 3, 4, 5, 6, 7 and 8. So you can traverse through any different direction. The only constraint is that you're not supposed to visit the same cell more than once. Okay, so the first problem is graph problem. Okay, so we need to somehow traverse through this matrix and find out all the different combination of words, and then we need to validate these combinations are a valid word in the English dictionary or not. That means the second problem is validating the word. How can we validate a word? Consider the interview has given these set of words. These are like about 6, 8. We have 8 different words in it. What if the interviewer doesn't give this valid word list? In that case, we have to use the English dictionary. English dictionary has about thousands of words in it, right? Maybe 10,000 or 20,000 of words. So traversing through each and every word to find a valid word is a time-consuming process. That is not efficient. So what we need to do is we have to find a solution to this. Okay? Let's discuss in depth about the graph problem first, and then we go to the validating word problem. So the first one is graph problem. If you see this particular matrix, these words are interconnected. According to the rule, you can traverse through different direction possible from any different cell in the matrix. Say for example, if I start from this cell, how do I traverse this way, and this way? To find a different combination of words, what should I do? Once I traverse to this particular cell, I have to keep traversing to all the different possible directions. That means we are somehow traversing to the depth of this particular graph. That arrives to the solution called DFS. Okay, that is depth first search. What you need to do is to find all the different possible combination of words, you need to do DFS, that is depth first traversal. Okay, that is depth first search. How do you do that? So from each and every location, try to traverse, like try to do DFS to all the possible locations in the cell, in the matrix. Okay, that's it. Moving on to the next problem. How do you validate a word? Okay, to validate a word, we need to build a data structure which can accommodate all the different words given by the interviewer or the words which are there in the dictionary. What is the solution to it? We have to use a try data structure which is very efficient in saving a lot of words and then looking up for that word by letter. Let's build try data structure for the given list of words. Okay, how do we do that? Every try data structure starts from space as the word, as the starting node. Okay, consider this is a space. Space has how many nodes? Space can have as many nodes as many letters in the English alphabets. That is 26. But in our case, it can be of different unique starting letters in this word. That is, we have a word starting from ant, that is A, okay, and then N, and then we have T. We have another word which starts from B, so B, there is only one word, Y, T, and then E. We have three words starting from C, that is C, A, we have T, and we have can, and we have car. Okay, and we have one word starting from D. Okay, let's write that here. C, D, O, and then G. Okay, we have two words starting from T, that is T, A, N, and then K. And there is one more, tube, U, E, and then E. So this is how the try data structure look like. But one thing we need to remember is we need to check when the valid word ends. In this case, the valid word ends over here, that is A-N-T. Okay, let's mark a valid word, ending valid word with some kind of Boolean flag in that particular node. Okay, so byte ends here, and then this ends here, this, and the dog is the valid word. So valid word, this is a valid word. Now that we have built our try data structure, let's try to run some scenarios on this matrix and figure out the valid words using try data structure. Okay, let's start from the very first cell in this matrix, that is 0.0. The letter is C. Now from C we have to figure out all the neighbors available. So in this case we only have three neighbors, that is A, J, and V. Okay, what you need to do in the depth first search, you need to keep going with the first branch or the first neighbor and keep going to as depth as possible. Now before going to the depth, what we need to do is we need to keep calculating the combination is available in the try data structure over here or not. Okay, so now the combination over here is CA. Okay, before checking in the tree, one more thing we need to maintain is we have to maintain the list of visited nodes. That is, let's maintain the visited nodes over here. So now we have visited C, that is 0, 0 or C. Okay, I have added that. Once you go to A, we need to mark it as, say, A is at 1, 1. For simplicity, I'm going to just mark the letters over here. Okay, we have visited C, we have visited A. Now the combination is CA. Okay, go to the C node from the space, go to the C node and then check, and first go to the C node and go to the A node, check whether that combination is a valid word. It is not a valid word, but it has the entry in the tree, and it can traverse down to figure out more words, and this chain is still valid. So that means that we can still traverse ahead. Okay, from the A, get all the possible neighbors to it. The possible neighbor is, since we have visited this node, we have already added, and we have the only possible neighbors we can visit is the J, Z, X, D, N, X, and V. We can't visit C. Okay. Now from A, the possible nodes which we can visit is J, Z, X, T, N, X, and V. So what we need to do now is, first let's go to this particular cell or node and then keep traversing ahead. Before doing that, what we need to do is add it to, so J is in 0, 1, okay, add it to the visited array, and then go here and check this particular combination is available. Since we know we are already in here, okay, let's go ahead and check the combination CAJ is available in the trial node. That combination is CA and J is nowhere available, okay, and the tree is not even continuing. That means this combination is not a valid word, and there is no point in going ahead or traversing ahead from this particular node, because we don't have any growing tree from CA and there is no entry of J. That means that there are no valid words which will be available. So there is no point in doing this. So stop the traversal and go to the next possible, that is CAZ. Okay, so now add it to the visited node. Z is at 0, 2, add it to it, and then go to the tree and then check for that particular combination. Since we are already in here, that is CA, check for Z. So there is no possible valid word in here, so this is also not possible, so we can just cancel this out. So this is done. Okay, now let's go to X, add X over here. So X is at 1, 2, so visit it, check here, this is also not possible. Now check CAT, okay, add it to visited, that is, so 2, 2, that is 2, 2, and T. Check for this combination CAT, here CAT, and this dot represents it's a valid word, okay. That means that we have found a valid word, okay. We can add it to one more array. The valid word we found was CAT. Okay. Now this is done. Okay. That means we have found a valid word. But the possibility is that we might have even more valid word which continues from here, like caterpillar or something. If the interviewer has given this word caterpillar in there, we could have had the try keep growing even further beyond CAT. But unfortunately we don't have. But still it's a valid word, right? So we have to consider all the different neighbors from T, that is A. Since A is already in the visited node, we're not supposed to consider that. We have to consider X, B, U, K, N, A, and N. Okay, and keep traversing the same way. What is that? All the possible neighbors to the T, and keep doing the same thing. But in this case, since after CAT there are no valid combination, there is no need to further traverse, further to do DFS. Okay, we can go to the next neighbor, that is CAN. Let's go and search CAN, and it is also a valid word. So we have to check the further combination, and here also there are no further combination. So the possibility is that we don't need to traverse from CAN node, okay? But you can add it to C, A, and N to the valid word list. Next is CAX, is not possible. CAB, it is not possible, there is no need to traverse. Similarly, you can now, CA tree is completed, now you have to go for CJ combination. Now CJ, okay, is a word, check for validity, okay, CJ, add J to the visited node, and then CJ, there is no presence of CJ in the try, that means that you don't need to traverse from here. Go to the next one, that is CV, we don't have CV here, there is no point in traversing. That means the traversal for this particular node is completed, okay. Now we need to go to the next node and clear all this off, okay, clear all this off and then start fresh, okay. What you need to do is, after clearing this, from the J node, what are the valid neighbors? C, V, A, X and Z. That is C, from J, we can go to C, okay. Now let's traverse from the next cell, that is J. J, what are the possible neighbors over here is C, V, A, X and Z. C, V, A, X and Z. And now what you need to do is, now go to check this combination in this try data structure. Are there any words starting with J? Okay. Even before traversing through this thing, first thing is go and check whether any try data structure available for the J. Since the J itself is not present, there is no point in searching for a word because there are no valid words which are starts from J. That means that we don't need to traverse any of these neighbors, okay? Now let's go to the next one, that is Z. Do we need to traverse? Since we don't have any of the words in the try starting with Z, there is no point in starting. Similarly with E, similarly with V, but when we go for A, there are valid words. What we need to do is, from A, there is valid word, get all the possible neighbors, that is all these 8 neighbors, C, J and etc. etc. Keep repeating things until you come to the last cell K. Once you arrive at here, that means your valid word list would have had all the valid words like cat, tube, can, and time. You can check by writing your code that you should get for this particular matrix, you should get cat, tube, can, and car. And I think car is not a valid word, so you should get cat, can, and tube, and tank as a solution. Okay, it's that simple. Okay, now what I have done is I have also implemented the same solution using Python as a programming language, and the link is available in the description. Let's try to understand what's happening in Boggle solver code. This part over here is all Python imports, which imports default data to build nodes for the try data structure, and LTK corpus words to get all the valid words in the English dictionary. We can use stop words to remove some of words like if, and, or, etc. and tokenized use to do the same thing. So this part of the code is to get the English word dictionary uncommented if you don't want to have this set of words to be figured out in this given Boggle. Let's go and see exactly what's happening. So in here you can see there is len c and len r variable which is initialized to the number of columns and number of rows. Instead of taking x and y as a reference, I am taking row and column. That makes our life easier. So these lists are considered as rows, and this is considered as column. Okay, to get to particular cell, what we need to do is boggle of 0 reference to this particular list, boggle of 0 of 1 reference to this particular element. That way we'll be out of confusion. So this try node over here is initialized to a very empty node, and valid keyword or the valid key gives us the information whether this particular um, try node ends with a valid word so far or not. And the next key contains the try node for the next nodes. In here, I have a list of tuples which is used to compute the neighbors. Given any particular cell, if I want, say for example, this particular cell M, if I want to compute all the neighbors, that is 8 different neighbors over here, we can just add these coordinates to the cell position of this particular M, letter M. We will get all the position of these surrounded 8 different neighbors. I have also associated with directions, which is a Unicode character. That means that we have to run with Python 3. The boggle code, the interesting thing with this code is this boggle code will also tell you from what cell and what direction you should be following to get that particular word. Okay, this function gen try over here generates a try data structure for any given word and updates the given node of try data structure. If the word is not a valid word, it just returns. If the word is valid, then what it does is it keeps adding the node recursively. Okay, so this is how it does. The valid key will be updated with whether that word is valid or not. The word can be only valid if only when it reaches to the end of the word when it is doing recursive iteration. Function over here, build try, actually loops through all the words which we give and then calls the gen try function to build the try data structure. So these two functions over here is used to build try data structure. And this function get neighbor over here, given a particular cell's row and column indexes, it gives out all the different possible neighbors around it. And this particular, if you see here, we are looping through the neighbors delta, and then we are just adding a row with a row delta and column with a column delta to get the new row and column ID of the neighbor. But the catch here is the new row and column ID can go out of the actual matrix, either go to the left, that is negative values, or it can go to the right side, which exceeds the length of the matrix. That's why we should have a check sure that we don't have an invalid indexes or neighbor indexes. Next, going forward, this code over here is what exactly what we are supposed to do in DFS. Given a particular row and column index and already visited list, and given a try node, and the DFS keeps searching or keeps going in depth to figure out all the different possible words. The now word always contains the previous so far traversed word, and the direction contains the direction at which the word particular is going towards. If the row and column index is already in the visited list, then we don't need to do anything, so we just written. And in this line we are getting the letter of a particular cell or given row and column index, and then once we know that we have crossed this if condition, that means that we are doing process, we have to add it to the visited. If the letter is in the try, given try, then only we can go forward, otherwise we don't need to do anything. So if this condition doesn't satisfy, all it does is it just returns from this function. If it's satisfied, that means that try has a valid tree starting from that letter, and then it adds to the now word so that we have a complete word which is tracked when we are doing recursively. And also check whether given try with that letter has a valid true, that means that we have arrived to a place where the traversed letters forms a valid word. So we just need to print that we found a particular word and print the direction which we have traversed so far, so that we know that to get a particular valid word, on what direction we should follow. So once we reached a particular node, what we have to do DFS is get all the neighbors and keep digging deeper. So get all the possible neighbors for the given row and column index, and then keep calling the DFS function recursively. Okay, that's it. In the main function, what we are doing is we are generating a try node for all the given English words, and this was initialized to an empty node. So when we call this function, all the English words will be loaded into this particular try node. Here we are printing the given boggle board, and then as I already explained, that we should be doing DFS for each and every cell in the boggle. Then only we can get all the possible words which we can form. That's what exactly we are doing. We are looping through exact number of rows and columns, and then we are getting every letter here just for the sake of updating this direction string, and then keep passing the row and column index to the DFS, and DFS internally does the recursive function calling to figure out all the possible direction. And that's it. It's time for demo. Let's go and run the demo. So when I do run this using Python 3 interpreter, we get output like this. So the given board is this, and what are the different valid words which we have found so far is cat and cats. We have, if you can see here, we have found cat and cats 2 times. Either we can make it unique using set in Python dictionary, otherwise we can print it as it is. The reason why we are doing is these solutions are a little different. So we can form cat in the given boggle with 2 different traversal. One is from the cell 0, 0, we can go diagonally, like from cell 0, 0, we can go diagonally downwards, that is CA, and then you can go diagonally upwards to form cat. So CAT, here you can see C, A, and T, or you can, one more solution which you got for cat is you can go down and go right. So from C you can go down diagonally and then go rightwards, so we can form cat in 2 different possible. So that's what it is giving. So we can also, it has also found cats that was there in the given list, and it is a valid word. Sign, it has found dot, man and mood, sick, pickle, etc. I hope this is working as expected. Solving boggle problem using DFS and try is one way of solving. This problem can be solved using different solution, different kind of algorithms and different solutions. If you like this video, please subscribe and share it with your friends. Thanks a lot.